morning, engineering 2. Woo! So let me go see if I can find my cheat sheet. There is a cheat sheet that I want to, I think it's this one. Cheat sheet that I want to talk about today. Let me see. This one. Okay. It should be part of your cheat sheet package. This one that you guys see here is just colored, but the cheat sheet package will be something similar. Okay. Okay. So now let's talk about GD&T. Okay. So let's do a little review before we start, and then we'll start on the next topics. If I recall correctly, and here I have a couple of notes that I was taking. We said that GD&T was a language, and the language that allowed for design to communicate to the manufacturer and as well as to inspection. For the inspection to also understand what manufacturer needs to do and also understand design, what they want, right? What these guys should be checking for. Okay, so it is a communication process. So think about it like a language between it. The example that we did at the beginning of the class when I introduced you guys to GD&T, it is a part with a function. In this case, it's just as simple as a spacer. We talk about regular tolerances, and I say if I want to reduce the tolerance, it's just going to cost more money. So instead of doing that, I introduce you guys to the language which has two components: the dimensional tolerances and the geometric tolerances. The geometric tolerances focus on the function itself, how flat I want it, and how parallel I want it. We could put some notes, but instead of putting notes, we say, you know what, we are going to be using GD&T. GD&T will give us the tools for me to put the language on the drawing. We talk about features of surfaces and features of size. We talk about datums, the theoretical perfect datum where everything gets to be measured from. You have three types of datum: feature datum, theoretical datum, and the simulated datum. Simulated datum get to be much better than the part in itself. If I were to rotate this one right there, you guys can see it. This is my granite table. This guy is my part. My granite table, it is 10 times better in terms of surface than my part. I think probably 100 times better. I don't know. Really much better. My granite table that I have here is calibrated to 1/10,000th of an inch. Right. Okay. And the last thing I believe we say, you know what, the way you speak of the language is when you speak the language is through the control frame, the feature control frame. The feature control frame is what you speak the language. You have a geometric characteristic symbol. You have a geometric characteristic symbol. You have a tolerance. You have a modifier. By the way, we also talk about the modifiers: maximum material condition, least material condition, and regardless of feature size. You gotta put a datum, especially if you're going to relate to something else. For example, the example that I gave you. I say, you know what? What about if I want to locate this hole? What is it going to be positioned with respect to what? Right? What is going to be the location? Okay, that's pretty much what it's telling you. Okay, the what? Position to what? All right. Let's continue here. Okay, now let's see. Do I have more lingo? Do I have more definitions that I need to go over? Okay, so what you guys see here, it is examples of the feature control frame and what it actually tells in simple words. Again, remember, it's a language. Well, the first one, it says the symbol of flatness, and it has a little 0.002. So it tells you the part of this feature has a flatness that must be within 0.02 of an inch. This feature has a circularity within 0.05 millimeters. This feature, it is parallel to datum A within 0.03 of an inch. This feature has a position at maximum material condition with a tolerance of 0.03 with respect to datum A, and datum B a maximum material boundary. Here is another lingo, maybe a little bit out of order the way I say it, but say the same. The position of the feature's axis must within 3 at MMC relative to the datum feature A and datum B at MMC. The new code does not call this M on the right side, doesn't call it MMC, call it MMB, and it stands for maximum material boundary. So you guys will notice that I call different MMC and MMB. Okay. If you guys were to draw this by hand, these symbols actually have a size, and you will have to adhere to this standard in terms of the sizes. You don't have to actually do it by hand, but if you, for whatever reason, maybe you have to do it in AutoCAD, where you will have to create these symbols, then this is how you would do them. The X stands for the text size. For example, if the text size is 0.125, this distance right here will be 2 times 0.125, so a 1/4 inch. And you will do the same concept for all the circles, the flatness, the cylindricity, the circularity, orientation, profile, location, run out. All of these symbols will have to have a certain symbol. Okay. You guys are not going to have to worry about it because we are going to use an inventor, but it will be a good idea in case you guys ever need to do a symbol. You have the sizes of how to make the symbols. Let's go to the next one. Placement of feature control frames. How do you place it? Well, you gotta first find out what you have. Do you have a feature of surface or do you have a feature of size? For example, let's suppose that I have a feature of surface. So let's say feature of surface, let me make a box. This is, and I want to put a hole. This guy is a feature of surface, okay? As well as this one, as well as this one, right? If I were to call out the diameter of this is a feature of size. If I want to graph the width of this is also a feature of size. Okay. Now, in the drawing, how would you call it? Let's suppose that I got a couple of views, right? So I want to say my box in my top view will look like this. My front will look like this. My side view will look like this. And let's make a couple of hidden lines. Hidden line, center line, bullseye, right? So let's say that I want to put a datum. I want to put my datum, and I don't know what I'm going to put. This is what I'm going to do. No, I want to know how to put this feature control frame on a feature size. So again, this is the feature size. If I want to do the feature size, which is in this case is the top, I want to mark it. I want to make it top. Actually, top is this one. Top is here, and top is here. Okay. So the way you would, it's not the top one. Okay. Not this guy that I wrote. This is the back. This is, and again, if you don't see it, this is top, front, and side view, right? So the top is here instead there. The way you will call it out, you can come over here with an arrow, and you will have is a box, which is my feature control frame. Then you would put, maybe I want to make this like flat, right? And then you gotta say, okay, how flat am I gonna do it? I want to say 0.001. Okay, flat within 1,000 of an inch. To be honest, I don't really like these arrows. The best way for me to do flatness, I think it is much cleaner if you just create an extension line and then you put the symbol there, 0.001. Okay, again, turn away from this. I don't really like it. I'm really picky, so I show it to you because many books will show it that way. I don't think it is. Let's not call it that it's incorrect. It's not appealing to the eye. Right? You want to keep your drawings as clean as possible, right? And I think keeping them like this is nice and clean. What about if I were to want to do my other feature surface here, right? In this case, is my left side. Well, my left side, let's say that I want to make it blue. It's blue. And let's suppose that I want to also make it flat, or maybe I want to make it perpendicular, right? I want to make it perpendicular. Remember, this is the top. This is the side view, right? Top and left side. Let's suppose that the left side, I want to make it perpendicular. Well, I can do it on each of these sides. Again, I could say that I can put a line here, an extension. I can make a feature control frame. I want to make it perpendicular to, and I gotta tell perpendicular to what. So if I want to make it perpendicular to something, I need to tell it to what. And in this case, my perpendicular to what would be the top of the part. But in order for me to give it to what, I cannot do I cannot do perpendicular to an imperfect shape. I have to do perpendicular to theoretical perfect. So I gotta give it a theoretical perfect. And the way I can do it is by giving a datum. Then I can make perpendicular to what, which in this case will be the top, right? And then I gotta tell it, okay, so how much tolerance I'm gonna give? Let's say let's do 2,000 inch. And so for now, you guys will see the placement. I try to keep it clean. You can also make errors, but I don't like errors. If you guys were to do like a feature size, which in this case I have a hole, you will put the dimension. Let's say this guy is 1.00, 1.000 plus minus 0.001. So you have to put the position, in this case is the one, the feature size. The feature control frame has to be where you have the size dimension. You can have a size dimension here. If you like to have a width, you will have the width right there, and then you will put the feature control right there. Okay. You want to keep your features of size, and your feature of surfaces. Make sure that you move away from any dimension. If you are doing a feature of surface, you don't want, for example, if you were to have a dimension here, you want to have a dimension there, you want to move this away from the dimension. Okay. So otherwise it means something different. So we will talk about what's the different. Again, extension. Here I have another, this is a feature of size. This one has a size, you can see 0.375. So you want to have the feature control frame right next to the size. Okay, I think that is a good start for us in terms of vocabulary and a couple of terms. Let's actually start with GD&T. The first thing that I want to go on GD&T is I want to go over the form. The form, it is meant to be used as a refinement to your part itself. Think about it like a refinement of a surface or a refinement of something. Okay, let me give you a little example. So let's suppose that I have my part, okay, and let's say that my part has a lower limit and it has a upper limit, okay, upper limit. And let's think about this like my tolerance zone, right? It could be as small as this, as big as that. If I were to leave it as is, my part could deviate as much as to make this guy pounded, or maybe like up and down, right? Uh, I can only have form as a refinement, but there is a rule, and it is out of without even just by using GD&T, it is a rule. We call this a rule number 1 of GD&T. And you can, it is actually like a big couple of paragraphs, it's only like two, 3 paragraphs, but I can summarize it in a couple of words. And that is perfect form at MMC. This is my summary. Perfect form MMC. This is pretty much what it's telling you. It's telling you, you know what? If your part gets to become at LMC, let's say that the part came like this, small, right? You can have a variation, and the variation has to increase all the way, well, I could increase all the way in terms of variation of form discrepancy as far as you get to the upper limit. Let's call this guy external feature. So this guy will be my MLC, this guy will be my LMC. Okay, the biggest I can get, the smallest I can get in terms of material, right? So your form can deviate all the way from LMC towards MMC. And once you get to MMC, you cannot have no more variation. Now, let's put this into perspective. Let's say that I went over here and I put my feature control. Let's put it here. Let's say my feature control frame, and I say, you know what? I want flat within, I want to have flat within 1000 of an inch. Okay. Right. Now, let's suppose that the part came here. Right. Also, let's suppose that the part came here and it looked like this. Right. So they will say, you know what? Okay, so it seems to me that is above the lower limit and it is below the upper limit. I will check it with a diode indicator, and the way you will do this is actually like 2 parallel planes that are 0.001 apart. 0.001 apart. Okay. In this case, you guys will notice that I have wiggle room. All the way I could go a little bit lower, a little bit higher. But as my part is getting, let's say that now my next part that I came, it actually came maybe somewhere here. All right. Okay. At that point of time, my 2 parallel planes, maybe one will be here, and the other one will be there. Now I still have this 0.01 because it seems to me like it's a little bit smaller, right? But now let's say that my part, all the variation that I could have, for me, the one that is the part that I came right here on the top, it cannot have 0.01 anymore because it cannot surpass the maximum material condition. Maybe what I can have, based on this condition, maybe I can have only 0.00, let's say 0.001, because I'm really close to the maximum material condition, right? Once I get really close to the maximum material condition, my limit of size restrain me to have more form variation. In other words, if my part wants to come at maximum material condition, right at the top of it, it cannot have any more variation in form, like more wiggly, because if it has any variation because it's already at the biggest I can get, then it will violate rule number 1. So rule number 1 says, you can move away, your tolerance, your form can vary from lower limit to upper limit. And as you move closer to MMC, you cannot surpass MMC. Your maximum variation in form has to stop at MMC. In other words, perfect form at MMC. Think about it like an envelope, and you go and you put a letter inside of it. You put the letter inside of it, it has wiggle room. As long as my letter doesn't grow bigger and bigger, gets to a point that is exactly the size of my envelope, and I cannot move it. So my envelope has to be perfect, because otherwise it cannot have any form variation. It's already gotten all the way to the envelope. Sometimes rule number 1 also will call it, you will also call it the envelope principle. Now that you guys understand, or we have talked about rule number 1, then we can talk about form tolerances. Form tolerances are a refinement of the already size tolerances. So in other words, you already have a form variation, right? Just by using your regular plus and minus dimensions. That's it, just by doing that. This is a refinement that allows you to create these 2 planes in the middle to refine the shape of it. So think about it, like your size tolerance already does this for you. The form geometric tolerances, all of these guys that you see there, they're just a refinement. Okay. For example, let's read the form tolerances definition. All parts include shape and surface variations. The amount of variation of individual features is defined by the size tolerances, the plus and minus that you put already there, and may be further specified through the application of form tolerances. Say, you know what? If I have something that is circular, something that is circular, I'll give you as much examples as possible. Let's say that I have a circle, right? It have an upper limit and it has a lower limit. Right? Then my part got to come maybe at this size, like this. Right? Still into the upper limit and the lower limit. Okay, so maybe you don't like this potato chip shape, or you can actually even make a square, right? You say, you know what, I want to refine it. And the way I'm going to refine it is by not only using the little one, the 1.00 plus minus 0.01, it's 0.03. I want to keep this guy at the size at 0.03 over 2, 0.03 over 2, 103 one direction and the other direction. Let's say that I want to control this variation, and the way I would do it is by putting a symbol. In this case, is circularity. So we do the same concept. You create like two. Think about it like a disk into the space. It looks like this, and then your part, all this wiggly line will have to leave. And again, this one's going to be skinny. Your part gets to leave within it. Okay. So this skinny red. This is meant to be the one that's here, right? So I'm controlling. It's a further refinement to my size tolerances. The orientation and profile tolerances also establish form requirements when they are applied to sources. Yeah, we will not do profile tolerances. That's out of the scope of the class. It's actually a little more complex. If you guys want to actually learn this, you will have to take a class where all we do is talk about this GD&T. And again, the TTEC 34 will be the one that will get you certified and ready to go in this, because we talk about it the whole semester, so much more time. Okay, what do I have here? Continue. It is coming its way. Coming. Man, this computer. Okay. The use of the form tolerances is desirable because it is easier to control the form of a surface, such as flatness. Again, it is a refinement. Because smaller size tolerances do reduce the permitted form variation, and may be seen that form tolerances could be eliminated by using smaller size tolerances to achieve the desired form control. Controlling form variations to excessive small size tolerances has the potential unnecessary increase in price. This is exactly what I told you guys at the beginning of the class, right? If you have this type of shape and you want to reduce the tolerance of the size, will cost money. It is better to do this. That one will control the function of the part without, while still keeping this size tolerance as big as possible, right? By controlling the function of the part in itself. Here are some of the form tolerances symbols. Let's see, form tolerances. Come on, computer. So the form symbols there are flatness, are flatness, straightness, circularity, and cylindricity. And again, the only thing that they control is the form, how wavy it is, how flat it is, how straight it is, how circular it is, how cylindrical it is. It only controls the form. Okay. Flatness, that's what it does. Controls the flatness in itself. The way you will call it out, you will do it with, I think I already told you how to call it out. I actually like the extension line better. You guys will notice that here I got 5/1000 of an inch. Okay, plus a 0.5 plus minus, I think this one is a 3. No, 5/1000 of an inch. Okay, so if you guys want to just do the size, can I have a better drawing? You can have as high as 0.505 and 0.495 for the LMC. And if I want to call out this flatness, then my part gets to live within two parallel planes. Actually, the tolerance zone for flatness is two parallel planes, which are separated based on whatever the feature control frame says. In this case, it says that we're going to be two parallel planes at 0.03 apart. So now I'm controlling the form alone. Keep in mind that I'm not controlling the orientation. I'm just saying, hey, I want the surface to be flat. So these flat planes, these two planes that are parallel to each other, can live anywhere within this yellow zone. Because I'm just saying, you know what, the surface needs to be flat. Can be like this, can be like this, can be like this, up, down, twisted. But as long as they fit within this yellow zone, which is the MNC and the LMC, you are controlling the form. How do you verify flatness? Well, if you guys were to look at flatness, the only thing that I'm controlling, it is the surface of it. And again, the surface in terms of form. So my part could be as twisted as this, as long as my tolerance zone of flatness, again, this is the parallel planes, 0.003. That means when my part came, here is this blue part, right? I just make sure that the surface that I'm calling flatness. And again, the red will not exist because this is how my part came, right? And my part has to be between let's call this guy the lower limit. Let's call this guy the upper limit, right? So my part came anywhere between lower limit and upper limit, which it passes, and my flatness, which is my part in itself, which I'm controlling the flatness, it came like this, the blue part. So because I'm not controlling the orientation with respect to nothing, I'm just controlling the form. The way that I can control this is I can put it upside the way I have it here, and because I don't have the control, and the way that I do it is with a dial indicator, something that looks like a dial, right? And this is spring-loaded stem that it actually touches the part. So it moves up and down, and it tells you what this guy's dial is not supposed to move three little lines. These guys are 0.001 increments. So the line will not have to move more than three little lines as I were to move my part. And I gotta shim it because I don't have an orientation. It is just the form. So in order for me to be able to go like this, if I want to have something that is flat like this, right, I need to shim it, or a bunch of shims here, so it's kind of like flat, and then I can now move my indicator. Okay. Another way to do it as well, you can put a hole on the granny table, and then at that point of time, my dial indicator spring-loaded stem will point upwards. Then I can put this on top of the granny table, and then I just slide the part. Datums. Let's see if I can. Datums, I think I already briefly talked about them. But before we talk about datums, and the reason why we want to talk datums is because we're going to move from form. This is your cheat sheet, which tells you many of the things I already talked about. One, the parts of the feature control frame. Two, what's a datum and what is the symbol for the datum. The datum reference frame, we can already talked about it when you guys were doing your dimensioning. I told you dimension from the datums. Bottom, left, back. The tolerance zone, I always think about like a region, okay? The tolerance zone is listed on the feature control frame where all the points and the reference feature must lie, where the part is going to lie, okay? The ones that we talk about, it is flatness, right? And flatness can be applied with an arrow, and then you tell this, put the tolerance zone. There are two parallel planes. Your part gets to be somewhere in there. You can measure with a dial indicator, or you can measure with a CMM. It is a 3D tolerance zone or two parallel planes where the entire part entire surface must lie in. Okay, that's my review of flatness. If we want to talk about orientation, and again, we will not do all the four tolerances. We just really describe these ones. Here you can have circularity, flatness of the right medium plane, a little more complex topics, which we'll not cover here because this is not a GD&T class. Datums. We talked about it before briefly. I told you guys that they are what we measure everything out of is based on the theoretical perfect, which is this red line, but in reality, there is not a theoretically perfect line. So the way we subdivide this is by saying, you know what, the part, when I look at it, if I call it the part, let's say, if I come over here and I draw the part, the one that is there, the yellow one, it seems to me that looks like this. Seems to me like it looks like this. And if I want to go and put a datum, call it datum A, then I'm defining the datum, but in reality, there is no perfect datum. I will put my part on top of the granny table, and I will start measuring with the indicator, make sure that things are parallel to each other or they meet certain geometric constraints. The datum is any physical portion of the part, where the simulated datum is what the datum feature contacts. So let's call it the bottom of this yellow is this blue part, and we call it datum feature. The green part that you guys see there, it is my simulated datum, which is the granny table. And the red is what we call theoretical datum. We assume that everything is theoretical. In fact, everything measures that way, assuming that's theoretical. But we know that nothing is theoretical, nothing is perfect. So what we do is we want to do our best to mimic perfectness. So we take care of the part. All right, we have a most stable configuration. I give it flatness, right? So now I can measure from my datum. Let's say that now I can come over here, get a dimension, and I can get another dimension, right? Because now I have a datum, something reference, something stable. I took care of the bottom by making it 0.01 apart. Then I gotta check it, right? So I'm gonna grab this part and I'm gonna put it on top of a granny table. My granny table is this red one, right? Which in this case is this table, right? The granny table that you guys see there. And then at that point of time, I go and I measure from perfection. But that perfection it doesn't exist, so I want to make it better. And this guy is calibrated, the one that I have in here is calibrated to 0.002. So an additional decimal place in terms of tolerances. So I want to make this guy better. Certified to the tool room grade B. Much better than my yellow part. And usually based there is a different standard for in terms of inspection and datums that you're supposed to do your datum simulators at least 10 times better than your part. What do I have here? Datum reference frame. This is what we're looking for to measure from a datum reference frame. So we gotta take care of our frame just the same way that I went and I took care of this, my bottom. Well, we will do the same concept. We will use flatness, parallelism, and perpendicularity to establish our datum reference frame. Now, your part lives in 3D space, right? It lives in 3D space all over the place. And the whole idea is to lock all the degrees of motion. Once you lock all the degrees of motion, then your part will not move in space, and then you can start making measurements off of it. Okay. A good rule of thumb is to use the 3-to-1 rule, which pretty much says, you know what, I can go and I can get my camera to just see a little better. That's not what it is. I'm not sure if it's going to. I'm not sure if it's going to be able to see. I'm going to move my camera. Let me change this. Right. So for example, like that one, right? You see my granny table. If I were to put my part in the table, right? So it kind of like rotates around, moves to the left, moves to the right. But now it's on top of the table, so I won't do this, right? Rotate this way or rotate that way, or go in and out of the page. So that's 3 degrees of motion that I'm rotating. If I were to put an angle and put it against that angle, then the only degree of freedom will be in and out of the page, right? Again, I will not do this. I will not do that, right? So rotation, it doesn't go. And also translation doesn't move. Doesn't go both directions. If I have another one of these angles and I will put it on the back of the part, this guy will push against and then it won't move. So these are restrained 3 degrees of freedom, that one restrained 2 degrees of freedom, and the last one restrained 1 more degree of freedom. So there are 6 degrees of freedom. X, translation in X, Y, and Z, and rotation on X. Let's call it X. X. Imagine that you guys have 3 axes. Let's call it X, Y, and Z. So translations move up and down, sideways, and rotation, 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 right? So 6 degrees of freedom. So I'm gonna put down this before you guys get busy. For cylindrical parts, you can also, again, as I previously told you, you can define an axis using a chalk, because an axis doesn't really exist in space. The way you assume it is by pushing on it. An axis actually defines 2 mutual perpendicular planes. So if I were to look at this, an axis, this is a plane. Let's call that another plane. Another plane. And if you were to intersect both of the planes together, this guy is an axis. Alright, so an axis defines 2 mutual perpendicular planes. What do I have here? Datums and tolerance zones. Each of these geometric symbols, the ones that do orientation, this one's a little bit more out of the scope of the class. We'll talk about tolerances later, position tolerances later, a little more complex, and I want to first finish form before I can actually introduce you to position. The way you select the datums, though, the way you select the datums are based on assembly condition and function. That's pretty much it. Here I have a list. Define a functional relationship to another feature of the part. How you assemble things. The measurement with respect to the specified design datum as a functional measurement. Yes, you're going to be measuring things off of a datum, so you want to make sure that whenever you have a stable reference frame, you will get measurements from that stable reference frame. You don't want to have a wiggly part and start measuring from wiggly parts. You want to define theory. You want to take care of the surface, make it flat, make it perpendicular, make it establish it. So you have a datum reference frame that's stable. Lock the degrees of freedom that you are required for function. And then once you have those datums that define the 3 mutual perpendicular planes, then you can start making measurements off of. So it's based on functional relationship. A good general rule is that the datum feature has to be a physical feature that you can see and you can touch. Yes, just like an axis, you're gonna squeeze, just like the 3 mutual perpendicular planes. You set them up by actually placing this guy, right? You gotta place these guys and then you get your part and put it there. Right? There has to be physical, so you can actually check it, you can actually manufacture it when you put it in a CNC. Specifying datums on the drawing. The way you put the datum is just like I showed you before. You will put like a little like a black thing, and then something looks like this, and then make a box, and then you name it. Datum A, datum B, datum C. This is the datum of how you will draw it. You guys are going to draw it, and if you want to put it on the drawing, you will use most likely Inventor, and it will look something like see command computer. It will look something like this, right? If you are defining a datum as a surface, because remember you have features of size, features of surface, you can define the feature of surface, datum as a surface, like this. If you were to have a feature of size, like an axis or like a width, you will have to put it where you have the size. In this case, you have to align it because I have a feature of size, so my datum has to align with the dimension. Make sure that you understand the difference between feature of size and feature of surfaces, because they are completely different wherever you place them. They have different tolerance zones, shapes of the tolerance zones, and what they actually control. So make sure you understand the difference between feature of size and feature of surface. So when you define a datum, it's actually controlling what you are meant to be controlling. Okay, so now Next time we meet, I'll do a little brief explanation of parallelism, perpendicularity, and angularity. That looks like it's going to be next week. Actually, no, maybe I can do a little. I can do this. Give me a half an hour of the lab, and then I'll talk about this. So you guys have more time for you guys to work on your. And I think I also moved the lab, so it should be good. All right. So yeah, we will talk a little bit about parallelism, perpendicularity, and angularity, and most likely also do a small review on GD&T. Let me start my share. Good morning, engineering 2. Woo! So let's start with the lecture. So if I recall correctly, let me see if I have a couple of notes again. Took a bunch of notes. The first thing that we did is talk about the purpose of function, and we use a spacer to represent. We use a spacer to represent the function. We said, you can have a potato shape. We can reduce the tolerance, but that one will cost us money. GD&T, it is a well-defined language that will allow design, manufacture, and inspection to communicate with each other. If you want to know a little bit more about GD&T, take 34, which is GD&T. I usually prepare students to get certified by the ASME by the end of the class. And also all of the people that won the state. Remember the people that came and talked to you guys? Well, that's the class they took. We talk about notes that you can actually add to the drawing by saying, there is a well-established language, and that language is GD&T. Geometric dimensioning tolerances. We talk about MMC and LMC, the maximum material condition. We talk about how we call out the datum. We talk about the feature control frame. This box is called the feature control frame. We talk about flatness, if I recall correctly. We also talk briefly about flatness, that it has to live within two parallel planes, spaced apart based on whatever the feature control tells me, and they have to live within your upper limit and your lower limit. We also talk about the degrees of freedom. You have the translations and 3 rotations on your part, and I believe that will end it up. Let's talk about now orientation tolerances. Okay, let's start with parallelism. So when we're talking about parallelism, it's because turn on the light. So you want parallelism when you are controlling a surface with respect to another surface, but you cannot control parallelism with respect to a wavy surface, right? So you usually do not control the surface to another wavy surface, because then it will be like perfection. So usually what you do is you refer back to theoretical perfect, and theoretical perfect means datum, right? You say the theoretical datum. Let's call it A. Now that I have this theoretical perfect, then I can go and I can refer to other surface like this one and say, I want to make sure that this surface is parallel to this other surface. Okay. The tolerance zone for parallelism is two parallel planes, spaced apart based on my feature control frame. So put a section line, put a feature control frame, put a parallelism, put the size of your tolerance zone. What will be this guy's spaced apart, which is 0.01. And then you gotta tell, okay, so I want to make a parallel to what? So I gotta tell you to what. I want to say the feature control frame. So this is what it's saying. Your part gets to live within these two parallel planes, spaced apart 0.01 with respect to datum A. Again, these two parallel planes are parallel to the red theoretical perfect plane. Okay. Again, your tolerance zone gets to live within your minimum and your maximum, right? So remember that you have a size tolerance and you have a geometric tolerance. So let's say that the size tolerance is maybe here, and the upper one is somewhere there. So from here to here will be the lower limit, right? And from here to there will be the upper limit, right? And my tolerance zone is this blue, but within the tolerance zone, I have another geometric constraint. This tolerance zone will live within this other tolerance zone, and I can live and move up and down anywhere within that tolerance zone. So this is what pretty much you guys are seeing here. If I were to zoom in slightly, you guys will notice that these two lines represent the tolerance zone of the parallelism, and then here you have your minimum and your maximum. That's your upper limit and your lower limit. And again, the datum plane A is what I'm making this guy parallel to 2, right? You're going to make something parallel to 2, parallel to A, parallel to the perfection, datum A. How do you verify, how do you check parallelism? Well, parallelism is a little bit easier to check. You will have your granite table. You guys have seen the granite table before. So, granite table. That is my granite table, right? This one, granite table. The way I will check it, I will have my part. I will have my diode indicator. Oops. My diode indicator. My diode indicator will sit on the part, and then I will just move my part sideways. Well, my diode indicator. Well, my diode indicator, and again, I gotta set up a better. My diode indicator will move up and down, and move my diode. Right? This is pretty much what I'm trying to tell you, right? So you will move my diode indicator, move my part up and down, and will give me my deviation on my part as my diode moves or it thousands on an inch. And again, it's easier to measure parallelism than flatness because flatness, remember, is not controlled. Flatness. This is flatness. Flatness is just a control of form. Flatness. Flatness. So it only controls form. It doesn't control orientation. So because it does not control orientation to nothing, it's actually, this guy just wants to make sure that it's flat to itself. You don't go and say, oh, I gotta, it is harder, let's call it, you don't have to either have a granite table and then put a hole and then put your diode indicator on this point. It looks like this, and then you're checking this flat surface as I move it up and down. And this is my diode indicator. Or you can also put a couple of shins, right? But it's a little bit harder, right? This one, measuring this one, then measuring this one, because this one is, you just go up on the diode indicator and you move your part to sideways, right? Move it sideways is easier. For parallelism, it's easier. For flatness, it's a little bit harder. Okay. And this is pretty much what it's telling you. This one has an image of the comparison between flatness and parallelism. Come on, compute. All right. So again, this is flatness. In order for me to do flatness, I can also, the other way to do it, I can also put shins. And I will try to make this surface on the red as parallel as possible to the orange, and then I can move my diode indicator, right? But it's harder. Compare this with flatness tolerances, where the tolerance zone is bounded by two planes that are parallel to each other, but not necessarily to anything else. Again, flatness is just flatness to itself. So when flatness is inspected using the diode indicator, we have to shim the underneath of the part to minimize indicator motion. Yes. Okay. You can also control parallelism of other features. So what you guys will see here is parallelism of a part where I have an axis or a feature of size. You guys see here, feature of size. And I want to make sure that my feature of size is parallel to the plane on the bottom, right? Parallel to A. What is A? It is the bottom part, right? So it is a surface or theoretical perfect plane, right? Now, if I want to make something parallel, that is an axis, and again, this is a feature of size, which is a hole, which is a feature of size. So how do I make it parallel? Well, I want to imagine that this is the hole. You see this one? This is like upward. Yes, you see the hole? This is the hole, right? This is my datum. Imagine that this is my datum paper. When I call out a feature of size, my tolerance zone, or actually my axis, which represents the feature of size, will be somewhere there. And now, is this parallel to my surface? Yes. And if I were to rotate it this way, is it parallel? Yes. Can I move it this way? Yes. This parallel. All it's parallel, right? So the tolerance zone, when you have an axis to a plane, it is to parallel planes. You guys could see it right there, right? So I went. It doesn't matter where I located my plane, it's always parallel to my datum A. I can shift it sideways. It's kind of like having a plane on the bottom and a plane on the top because my axis can move anywhere. So when you have, let's call this by datum. When you have a datum as a plane, and you have a feature which you are controlling this guy, controlling an axis or a feature size axis, your tolerance zone is two parallel planes. Right? And again, you guys could see I try to explain you that. And again, we have a little image right there which represents my axis will always be parallel. You can also have a access to an axis. So if you were to look at the feature control frame of a plane to an axis, you wouldn't have. You come over here. You will have parallelism. You will have 101, and you will have datum A. That's all you would have. But if you have a datum, which is an axis or a feature of size, you are controlling an axis. Your tolerance zone will be a cylinder. So if you want to look at the feature control frame, to indicate the cylinder, you would put a diameter, because I need to know the diameter of the cylinder. Again, it's not datum A, but in this side, the datum is a plane, and in here the datum is an axis. So you will see 0.01. And if you guys were to look at this in a graphical representation, this is the axis, the feature of size. You guys can see it. This is the diameter. That's the datum. So a feature of size, which is represented by an axis. And I'm controlling another feature of size, another axis. My axis gets to live within the cylinder. You guys can see cylinder diameter. The parallel the access to axis parallelism. Parallelism of one axis to another may be specified as shown. The feature axis must be within the specified tolerance of location and must lie within the cylindrical zone of 0.005 diameter, regardless of the feature size, that is parallel to the datum axis. So again, this cylinder is parallel to this axis. Let's take a look at perpendicularity. Okay. Again, we put this guy, I'm going to call it parallelism. What about if I want to have perpendicularity? Well, let's now compare that as before. So before we did parallel to what? Datum A. So now let's do something else. Let's say that now I want to make it perpendicular. So if I want to do perpendicular, I will have my shape, and I have a part like this. And let's say that I want to make this face perpendicular to that one, right? But I cannot make perpendicular to imperfection. I have to make perpendicular to theoretically perfect, which I want to call this guy datum A. Okay. The tolerance zone of my surface, it's also going to be two parallel planes. Okay. Spaced apart by whatever the feature control frame tells me. So in this case, I'm going to make an extension line. I'm going to put a datum. I'm going to say that this is perpendicular within 1,000, 10,000s to respect to what? Well, perfection, to datum A. So this is 90 degrees with each other. My part gets to live somewhere in the middle. And the spacing of this tolerance zone, of these two parallel planes, is going to be 0.01 indicated with the feature control frame. Okay, that's pretty much what it means. Okay. The perpendicularity is can be applied to surfaces and to features of size, just like we did it with axes, using either another surface or another feature of size as datum. Perpendicularity are applied to surfaces using either a leader or an extension line. We don't like leaders, already told you I don't like them, so don't use them. This surface must be perpendicular within 0.012 relative to datum plane A. You guys can see it. I'm controlling this green surface, and I want to make sure that it's perpendicular to perfection, so I go to datum A. Boom. What do I specify it here on the drawing? Let me see what else do I have here. I probably should change my my PDF. I use like Acrobat instead of Bluebeam. Again, you can also do a perpendicularity instead of just doing a plane to a plane. We can also do a feature of size to a plane. So if I were to look at this guy, it's a different example. Let's suppose that I have, I don't know. Let's suppose that I have a surface that looks like this, like that, and within it I have a pin like that, and I want to make sure that that pin is perpendicular to this surface. Okay, and again, it could also be the bottom surface. Well, the way I would do it, I would put my surface. Okay, this is my front view of it. This is what I'm controlling. I'm controlling the axis, so I can dimension. That axis. Okay, let's call it. We can call this diagonal diameter 1.00 plus minus 0.01. But then I can control the geometry of this axis. I mean, this guy controls the size. The geometric tolerance zone controls the orientation. That's why they call it orientation tolerance zone. I want to make it perpendicular, and I'm going to call this guy datum A. Right, I'm going to make it perpendicular to datum A. And I want to make sure that the axis leaves perpendicular to this datum A. Well, the tolerance zone for this, it is a parallel cylinder that is perpendicular to datum A, and my axis gets to live within this cylinder. Okay, and again, the size of the cylinder, let's call this diameter of the cylinder, will be, I have to put a little diameter because it has a cylinder, and let's put here 0.01, like that, right? And this is what you guys see here. It's telling you, you know what, your size is controlled by this, and your perpendicularity of your axis is controlled by this cylinder, which is perfectly perpendicular to that plane. Okay, so let's put this in my cheat sheet so you guys could have it. We are looking at perpendicularity when you have a plane which is a datum, and you have a feature which is a plane. My tolerance zone will be two parallel planes perpendicular to each other. Right? You guys can see it. Two parallel planes perpendicular to datum. Let's call it perpendicular to datum. Right? Parallel perpendicular to datum. The way you will call out the feature control frame, well, you will do it like before, 0.01 to datum A, and datum A is a plane. If you were to have then a datum which is a plane, and a feature which is an axis like the one that we did, the tolerance zone is going to be a cylinder, right, which is perpendicular to datum plane, right, as I told you before. And the way you will put it in your feature control frame will be perpendicular, essentially perpendicular within 0.01. You gotta make sure this is a diameter, so you gotta put the diameter, and then we put datum, and this will be an axis. That's the one that we did here before, right? It's an axis. That's why I'm controlling the plane and I'm controlling the axis, and the axis has to be within a cylinder. That's why we have a diameter there. Okay. Let's go interpretation. This is same concept here. Kind of like already explained it, but it's good to have slides so you just go refer back to them. This is a plane to a plane. I have an angle in which I am controlling the back surface relative to with respect to the domain. So you guys will notice that if I want to have a surface, the surface has to be within. And then as long as it's within those two parallel planes, perfectly oriented, perpendicular to datum A, it all will be good. The surface must be within the specified tolerance of size and must lie between two parallel planes 0.005 apart that are perpendicular to datum plane. You can allow big size variations, but you are controlling the orientation and form of things based on your function. Yeah. How can you check a perpendicularity? So we talked about flatness before, but we also talk about parallelism. But what perpendicularity? Well, in terms of perpendicularity, you guys could probably see here. See if I can show you. So this guy is an angle, right? Like that, right? Just concentrate on this, you guys can see it. Put a little bit higher. Nothing mechanism here. Look at that. Okay. So you guys can see here. This is the. Imagine that here you have the. Right? So this is my part. This is my part right there, my part. And I want to make a check the perpendicularity. Let's say perpendicularity of this surface with respect to this surface. I think you guys see things backwards. Actually, it's pretty good. Okay, so let's suppose that you guys want to do that. So what I would do is I would put my part. Sorry for this. It's just that will not make much better sense. So let's suppose that I want to check the perpendicularity. Well, this is my angle, and again, you guys will see here is also part of the of inspection tooling. It is meant to be perpendicular within thousandths of an inch. So now if you guys were to put a part, put it against it, if it is no perpendicularity, there might be a gap somewhere in there. In fact, you can put a light, it might be somewhere there. That's why you go and you use filler gauges. Filler gauges is like just a couple of pieces of metal that you can stick in there within the little gap. And if there is a size that is bigger than your tolerance zone, then there is too much separation. So it won't be perfectly perpendicular, right? You will see something like a little gap somewhere in there as you shine the light. You can use filler gauges. Most straightforward method to check perpendicularity of a surface is a single datum surface with a surface plate or precision square and a filler gauge or the stock wire. So these are the filler gauges that I'm telling you. This is your part. This is your precision square. You put a bunch of filler gauges. This is your granite table. What else do I have here? You can also control perpendicularities of a feature of size. And let me see, I come over here, I have a nice picture. I don't have nothing to check you, show you graphically, but here you guys probably will notice that I have a part right there. And within this part, I can use the filler gauge, and this dial indicator can slide up and down, and it can tell me my variation in surface. It's also a way to do it. You can also do perpendicularity. Let me see, what is this one? You can do perpendicularity of two datums using two squares or two angles for precision inspection. So you guys can see it on the next one. So the same way that I did one, I can do both. I just gotta place my part with two angles. So you guys see this one is one, this one is one, and the one on the back is another one, right? So you can do perpendicularity to two datums. The same way that you did it to one, you can do it to two. So for example, how would do that one? So if I were to check something that looks like that, and let's call this guy granite table. Let's call this guy datum B. Let's call this guy. Actually, we don't have to call it datum B. We're just gonna say that I'm controlling the surface, right? So if I want to put a part that looks like this, right, and stick it inside this, well, the first most likely will want to control the bottom of the part, right? So maybe put some flatness on the bottom. That one will generate an unstable configuration. So I can call this guy datum A, right? And then right after that, maybe I can control the perpendicularity. So let's say it's a flat datum A. And maybe I can control perpendicularity on the left side. So perpendicularity on the left side, control it. And I can, after I do it, so I'm going to call it perpendicular 15.1 to datum A. So you will put this part, we'll pump it against, and then I'm going to call it datum B. After I establish it, I call it datum B. And then I can do something similar to this other surface. Let's make it red. You can do also this surface. And again, this surface can be perpendicular to datum B and also to datum A. I don't know if you guys can see it. This is datum, and I can also call it datum C if I want, right? And I'm controlling stuff with each other. And if you guys could really see this, right? Once it's done, I establish three perpendicular mutual planes. When in one, I went and I did flatness within one, and the other one I did perpendicularity to datum A, which is the bottom part. And in here I could have done the same thing. I could say, you know what, I want to make it perpendicular within point of one. I want to make it perpendicular to datum A, which is the bottom, and I want to make it also perpendicular to datum B, which is the side. So controlling things with respect to each other. Okay. Hope you can see. What else do I have here? Axis to a plane. So we are still doing, what is the axis? The axis is the datum, or is it the feature? Let's see what I got here. Okay, this is exactly the same thing that I told you guys. So I have a pin, I have a surface. My feature is a feature of size. You guys can see it. This is the diameter. It's a feature of size. And then I'm controlling the feature of size with respect to datum A. So it's a cylindrical tolerance zone. We want to talk about MNC. That is something that I want to cover next time we meet. Probably I have to talk about rule number 1, and then that will make a little bit more sense for this. Virtual condition. We also talk about lex time, and let's talk about angularity. The last one. So the same way that you guys can control a surface, the same way that you guys control, you can control flatness, you can control parallelism, you can control perpendicularity, you can control features of size to planes, or even axis and features of size to features of size for parallelism and perpendicularity. What about if you were to want to control something that is slightly different? So for this one, another one. Let's say that you have now a part that it looks something like this. Let's make this guy like that, something like this, something like that, right? This is my front view. And let's say that I want to control this surface, and I want to control it to imperfection. Well, I cannot control to imperfection, so I can control to perfection, and I'm going to put perfection datum A. And again, before that, I most likely will want to take care of the surface, and I might want to, the way you will do it most likely, let me do it on this side. You can also do it on this. So most likely you will go over here, make it, take care of the surface. So I want to take care of it with flatness, 0.001. And then after I have controlled it, now I can call it datum A. Right? Now, the whole idea is not to learn flatness, because we already talked about it. The whole idea is to take care of the surface that is inclined. Okay? I want to make the tolerance zone for that inclined surface, which is actually two parallel planes. Let's call this guy parallel planes. Okay. How would I call out this on the drawing? Well, I will have a feature control frame. A feature control frame. This guy actually needs to be pointed out with a leader. It's not like the extension lines. Okay, that one needs. Okay, in order for me to get the angle, I had to make an angle basic. And what is basic? It's kind of like just a square. And what it's telling you, you know what? I want you to locate these two parallel planes at perfection angle. Let's call this guy 45 degrees. Right? So it's going to be a perfect angle to represent these parallel planes. Okay. No little plus and minus or anything else, because I'm not doing the tolerance based on this angle. I'm making it based on this feature control frame. You will put an angularity symbol. You will tell me the size of your spacing of your tolerance zone or your parallel planes, which in this case I want to say also 0.1. And I gotta tell it parallel to what? I mean, angular to what? So I'm gonna make angular to datum A. And again, datum A is the red one, right? The bottom one. So now I am controlling the form and the orientation. The form is because it has to live within it, right? The waviness, and also the orientation of the surface with respect to datum A, which is the bottom of the part. Again, my part will get to live somewhere here, right? Now, keep this in consideration. It's different when you guys are doing size tolerances, because size tolerance is something like this. You do size tolerance, and you put a size, and you say, oh, this guy is, I don't know, 45 degrees plus minus 0.01 degrees. Another two dots there. This guy is telling you, you know what, you can have 45 degrees and you can vary plus 0.01 minus 0.01. So, right, so the tolerance zone, this is, your tolerance zone actually increases, as you guys can see. So this is different than this one. This guy is saying, you know what, I'm not going to control it with this. I'm not going to control it with this. I'm going to make it perfect. And then I'm going to let them know what I want in my feature control frame. Okay, this is very much what angularity tells you, which is exactly what you guys see here. Angularity to the plane to another plane is most commonly encountered situation. The tolerance zone in this case is the area between two planes, each at the specified angle to the datum. Make sure that you put a basic dimension you need it, right? Because my tolerance is based on the feature control frame, not in the plus and minus. Angularity representation. I think this is kind of like just a recap of what I just told you. Okay, you guys can see there, right? So two parallel planes, Right there, you have a plus and minus. So the plus and minus could be like this, or it could be like this. But again, my parallel planes are 0.09 apart all the time. 0.09 apart all the time. My part can live anywhere within it. As long as it lives within it, keep in mind that I'm not locating where this starts or where this starts. My whole part just has to live within it. Okay. Because I'm not controlling location, I'm just controlling orientation. And by itself, by default, you're also controlling form, right? You can see it, the waviness lives within these two parallel planes. So I'm controlling the form, then controlling the orientation with respect to that datum. The way you can do the verification, you can do a sign bar, do a couple of stacks of these little gauges, stack them right on top of each other until you get the angle that you want, and then you can use that for inspection purposes. So you see, I have a nice drawing here. You can tell you the inspection purposes. Right there, right? Inspection purposes, diode indicator. Another way that you can also do it, you can do it with a CMM. It's a computer measuring device. It's kind of like the diode indicator, but it's connected to a computer, and the computer will let you know what you want. Okay, now let's do a quick review. And actually, I want to do it with one little example. It's going to make up one example. Let's say I want to make up a part. So let's say that I have a part that looks like this. Over here, over there, this, something that looks like that, something that looks like that, right? And this guy is meant to be parallel, by the way. Okay. It's meant to be parallel. And let's say that in here I have a hole, and let's say that in here I have another hole. Okay. Well, if I were to do a part, I would say, okay, how am I going to build this? Well, most likely I want to set it up in a on a three mutual perpendicular planes, right? I will most likely want to do that. And I want to define this perpendicular mutual planes, right? So I want something to grab this part and stick it somewhere in there. So I have a 0, 0, 0. Okay, so let's actually come up with some views really quick. So let's say that my part will look something like this in the front. And if I want to do the top, it will look something like this. I have a hole somewhere there. And I have another hole somewhere there, right? And let's say that I have a side view, and the side view will look like this. Again, I have a bunch of hidden lines which I'm not going to show, but really are there. And again, for clarity, not because it doesn't have to be there, just for clarity. Okay. So now, let's say that I want to control this, and the whole idea is for me to put everything in this theoretical perfect plane. Okay. Well, I got to take care of the bottom, right? Step number one, because I'm going to use it, I'm going to call it datum A, and datum A is going to be my bottom of my part. I got to take care of it. So I want to take care of it by putting a feature control frame, and I want to say, you know what? I want to make it perpendicular. I mean, flat. Now I control the flatness of my part, and it's nice and dandy. And I kind of I'm going to use it to define other features. So I'm going to call it datum A. Oh, okay. I have defined it. Now I'm like, you know what? I took care of this, but in order for me to constrain the degrees of freedom on my part, I need to define this datum, and I want to define that datum. Well, let's define another datum. I'm going to call this guy datum B. And in order to define it and correlate it to datum A, I want to make it perpendicular to datum A. So what is datum B? It's here. I'm going to call it datum B. And if I were to look at it in my views, it will be this guy and that, right? It's the left side of the part. Well, how am I going to define it? Well, I can put an extension mark right there. I can say I want it perpendicular, and I want it perpendicular to datum A, right? And it's a plane perpendicular to another plane, which is the bottom, right? So I want to say perpendicular to datum A, and I want to make it perpendicular to datum A within 10,000 of an inch. Okay, so I am done with the bottom. I'm done with the left. What about the bottom? We'll go get me a different color. Let's say that this guy is going to be my back. I want to put it datum C. Well, datum C will be the back of the part, right? Which will be this one, or it will be this one, right? Okay, let's control it. I can go on this view, or I can go on this view and say, you know what? I want to make sure this part is perpendicular to datum A, right? Perpendicular to datum A, and I also want to make it perpendicular to datum B, so I have something controlled to each other. So I want to say perpendicular to datum A and perpendicular to datum B, okay? And I want to make it perpendicular with 0.1. You guys see it? Okay, now I have a mutual perpendicular planes, orthogonal perpendicular planes. I can grab my part, I can stick it in there. Now let's start controlling things. Let's control the bottom of it. Let's control this part, right? Well, I gotta measure everything from my datum first, from here to there, boom, boom. From here, gotta move this guy a little bit more this way, right? Because I cannot put it right next to it, but so otherwise I will need something else. I got that guy, I got that guy. I'm done. Let's go from the left side. Let's make this guy boom, 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 boom. From here to there, that is that one. Let's say from here to there, that is that one. Let's say from here to here will be this one. Let's say from here to there will be that one. Let's say from here to there. You guys see it? Everything from my datums. And finally, I can get this dimension, and I can get this dimension give me those ones too. And I can also get the diameter, blah, blah, blah. Right. Let's control things. Now that I got all the sizes, right? All of this is controlled by plus and minus, but I got to control each geometry. Let's take care of the surface on the top, which I want to say this surface. Okay, I got to control it, which is this one. And I want to make it parallel to datum A, which is the bottom. How do I do it? Control line, parallel to datum A, within 1. See, and I controlled it. I could do the same thing over here. I can control that line. And I can put another parallel to datum A. So datum A is this guy, and I'm controlling the surface within 0.01. I can also control the angularity of this guy, right? So I can control the angularity. I can go over here, each control frame, angularity, and I'm controlling with respect to this datum A. I gotta give it a basic tolerance, basic dimension. That's the one that has the square of the dimension. Let's say it's like 45 degrees. But guess what? If I'm gonna give this one, I cannot give you this one. So I cannot give you this one. Let's get rid of this guy because I'm controlling this. If I want to put the angle, then it becomes double dimensioning. Right? So you gotta be careful not to do any double dimensioning. So by me getting rid of this guy, then I can do this 45 degrees. Okay. Then I could say, okay, now I can do it with respect to datum A, and I can give it 0.01. So that's how you use it. Most likely, next time we meet, we'll do a couple more examples. But at the end of the day, is having a regular dimension tolerances and then apply function. And again, right now, I just made up the function. In reality, the whole GD&T will be based on function. You apply them based on function. Oh, I need this guy because it's going to be mating onto something else. It needs to be established, and I need to make sure that I control this parallelism, or maybe I can control its angularity, and so forth. Okay. All right. Next time we'll talk about something different, a little more GD&T. You guys also need to know how to position things, and also need to learn about rule number 1 a little bit more. Let me stop the share. Let me get the notes. Okay, let me stop. Good morning, engineering 2. Let's work on. Okay, so last time we met, if I recall correctly, I introduced you guys to GD&T. We talk about what is GD&T and what is the language that allows you to communicate within different disciplines. And then I gave you guys a couple of videos, which you guys should watch if you haven't watched, which I talked to you guys about form tolerances, what controls the form, the surface of it, the wiggliness of it. We also talk about datums and whether you use datums in there and how do you apply the datums so you put them in the drawing. Okay? So again, I really recommend you guys to watch the video. If you haven't watched it, please do so. We are going to move into something different, which is orientation symbols, a couple of them. So for that, we need to explain a little bit over here. So up to now, let's put some drawing here. Up to now, you guys have a shaft, and you guys have had a hole, and I have told you that you guys have a tolerance. Let's call it a tolerance here. Well, this tolerance is actually your dimensional tolerance. So remember, you got G, D, and T. You got D. This one is the D, dimensional tolerance. And what it pretty much tells you that I'm not accounting for the crookedness of the part. So this guy could actually be represented as if I were to have a part that looks like this. Let me see. Put a part, right? And because I'm not accounting for the crookedness of where this hole could be, my hole could be crooked maybe like this, like that. And for simplicity, for sake of simplicity, I'm going to make one of the sides perfect so that I can go and I can crooked, make the other one crooked. Let's say crookedness like this, right? Actually, no, let's make both of them crooked. Both of them crooked. This is representing the hole, by the way. You guys don't see it. It's the hole. It is crooked. In terms of the size still control. I can still have the MMC, which will be the smallest I can get. Let's put it here. MMC. And you'll still have the LMC, which is the biggest the hole can get. Right? And I can also have the center axis once I expand, use the same way that I go and I grab the bolt and I squeeze on it and I define an axis. I can do the same concept with the shaft. So in this case, let's grab the shaft, and my shaft can literally be quickener on the side. Let me see if I can go and extend this line out. And let's give it quickeness too. Quickeness. Beautiful. Right? And again, this is meant to represent a let's call it a shaft. and the one on the top is meant to represent a hole. All right. You guys will notice that my shaft will have the minimum I can get, which will be in this case the MMC, and the biggest I can get will can also be the MMC, right? The biggest for the material condition. Now, I have not accounted for any type of geometric imperfection. The only that I have accounted, actually this, it is a gross representation of what this is. Because the only thing I have done is I have made it such that it fits. What happens when I actually account for things that are crooked? That's what the G comes about. Let's make the G. The G, D, and T. So the G. Now, in order for me to apply G, I need to do D and G together. So let's say that I have a part that looks like this. And it has a, let's say, this is where it's supposed to be, right? Perpendicular to the surface, like that. But it's not actually perpendicular to the surface. Let's say it's a little bit off axis. So I want to make it a little bit off axis. And that's meant to represent the axis. Then I will have my part, which I'm going to make it like this. And I'm going to make it a little bit crooked. Like this, right? And again, this crookedness, this guy could also be crooked, right? It could be like that. And I put the exterior boundary to represent the maximum material condition. It will be like your pin, right? And let's say that I grab this part, this pin that is actually mounted to, another plate. Let's say it is weather or whatever that's the case. So maybe it's just a single part altogether. Okay, and I need to insert it into another part, something like this. So it's another part that looks like that. And again, it has a hole. If I were to make the part, and I were just to make a hole like this, right? So that I were to account for it, and I were to try to sit this on top of it, I couldn't fit it. Why I couldn't fit it is because now this guy, this face here, needs to sit flush with that face. So this point of time we have a big problem because now I cannot only use the D, I also need to use the G, which is the geometric imperfection. In this case, you guys will notice the geometric imperfection is a little bit on arrow angle, and it's called Angularity. And in order for me to be able to make this guy work, I need to have a combination of those two together, the G and the D. The D will be your MNC, right, which will be your maximum material condition, the biggest I can get. What about if I can also account for the crookedness I can get? Well, it seems to me that it started here. This is what it's supposed to be. And then actually it is somewhere here. So it's supposed to be here in the center, but it's actually crooked. So what I can do is I can say, you know what? Let's account for that crookedness, right? And I'm gonna put a little zone here. It's represented actually as cylindrical tolerance zone. My axis that you guys see here, which is actually what is being crooked, has to live within this tolerance zone. This tolerance zone is specified in the feature control frame. Now, if I were to put them both together, I'm going to grab the diameter that I just made my axis and where it has to live, and I'm going to put it, adding it together. So I'm going to have actually a boundary. You see a boundary that encompasses the combination of both of it. Let me see if I can make a boundary. Imagine a boundary here. This is my boundary. And I'm going to put it like this. This is my boundary. This boundary that I just made, which is imaginary, if I were to look at its size, is what we call it virtual condition. And the virtual condition, it is the effect of me accounting for the worst case scenario in terms of filling condition, the D, as well as the worst case scenario of geometric imperfection. So if you guys were to look at this little distance right here, that is the same distance that this one has, right? If I were to account for the maximum I can get and the crookedness I can get, the maximum I can get and the crookedness I can get, I can have the virtual condition. So the virtual condition is equal to the biggest, let's call it in this case for an external feature, so I have a pin, external feature. The worst case condition will be the biggest I can get, plus the crookedness I can get, or is equals to the MNC plus the geometric tolerance. And I want to assume that you guys could see that now I have accounted for both of them, and that my part should now be able to fit in here. Now, when I want to make my hole, I need to make it to the virtual condition so that the pin that I have now accounted for the worst case scenario, when it's crooked and when it's the biggest, I can make the hole to that virtual condition, so I will be able to guarantee assembly. When you put G, which is geometric imperfection, and D, you will get your total tolerance. Now, how do you apply this geometric imperfection? By the way, you can also redraw this a little bit different. I'm going to try to do it like this. Put one here, and I want to make an imaginary extra tolerance. I'm going to put this one here. I'm going to make an imaginary extra tolerance, and then I also want to make the real tolerance. So one is the imaginary extra tolerance, and one is the real tolerance. So when I have a pin, which is an external feature, my part needs to count for the biggest I can get. And I also need to add a little bit more, and the little bit more is going to be my geometric imperfection. So you actually have like two tolerances altogether. One, which is the dimensional tolerance, and two, which is the geometric tolerance. The total thing is what G, D, and T is, pretty much. In terms of features of size, right? Because we're doing features of size, things that have diameters, or things that make with each other. Now, in the problem of the hole, it's a little bit different though, because when I have a hole, and if I were to put a hole like this, let's say I make a hole that is crooked, like that, and I want to put a pin that is perfectly to the sides, right? And I try to put a pin inside of the hole, it will not fit. And why doesn't it not fit? Is because any type of crookedness that goes into the hole, it will actually generate a smaller hole, right? So how do I account for this? Well, I need to ensure that my hole, it gets decreased by the size of the geometric imperfection. So we're still gonna have MMC, we're gonna start have LMC, we're still gonna have the D, we're also gonna have the T. And this total tolerance that accounts for the hole will live over here. And even after I go and I make my hole smaller, actually make it, so this guy will be, let's say this guy will be the worst case condition, because I made it the smallest, worst mating condition. Keep in mind, if I make it bigger, which is LMC, my hole will get bigger. So I gotta make it smaller to LMC because my hole will get smaller. And let's actually also take away the geometric tolerance, the G. And even like that, that will be my worst mating condition. When I go and I count for the D and I count for the G. Now, the worst case condition is this one. And I use that worst mating condition so I can match it with the worst mating condition. Worst. The worst mating condition of the pin should be at least equals to the worst mating condition of the hole. And in fact, sometimes what you do is you make this guy a little bit bigger, shift it a little bit more upwards to allow for a little bit of allowance. I'm going to assume that you guys now would think it's really important for me to understand tolerances so you can understand this. Let's talk about how we apply this parallelism, how I take care of the G in terms of orientation. The way you take care of the G is by remembering that you have two things. You have features of surface and features of size. The features of surfaces are actually just surfaces. What I'm talking about, all this mess about me putting a pin and its sizes, this is just for features of size. Now for features of surface is much easier. It's all I have to say, you know what, I want the top being parallel to the bottom. And I give it a feature control frame that it has these two lines. And I need to ensure, by the way, that this little feature control frame is as far away from the dimension, so it will mean something else. And when you apply it to a surface, what it represents it is, I want you to make the surface that I'm pointing to parallel to datum A. Where's datum A? Well, datum A is the bottom of the surface, to me, the bottom of the part. So the top parallel to the bottom. The representation is saying, you know what, the bottom of the part, I'm not doing the bottom, I'm doing the plane, the theoretical perfect, the datum, which is something that if you didn't watch the lecture on Thursday, please watch it so you can understand this. So you go and you measure from the datum, you will have a tolerance zone of 0.009. My part gets to live the surface, the surface gets to live within it, the form of it needs to live within it. And it can move up and down. It can move up and down. It can move it up and down. It allows me to move it up and down within the size limit, which in this case, it is 4.48. That will be the biggest I can get. Now, what does this mean? It means that you have an envelope. This is a features of size. Features of size. For features of surface, it's a little bit different. It follows something that we call it rule number 1. And this is what it really means. It's kind of when you go and you have an envelope. And that's why they call it the envelope principle. If you want to have an envelope, and you want to put a letter, in my card, it is this size, I can grab and I can put the card within the envelope, and I will have a lot of wiggle room. This will be like if I were to have a pin and a hole. Actually, no. Okay, so in this case it is because it's a surface. Let's not do it like this. It's going to confuse you with the feature size. Let's just say you have the D. This is just controlling the D, okay? Because you're only doing the surface. If I want to put this card inside here, it will have a lot of wiggle room, right? And that it is bounded just by the D, not G. You got G, D, and T, right? We're only worrying about the D, which is the let's call it the lower limit and the upper limit, or where you come over here, which is the D, right? When my part comes out the smallest card that I could get, they can fit in here. If I were to come over here to the top, which in this case would be the MNC, my card would rarely fit. Okay. Now, if I were to come out the size when it was smaller, the card would have the ability to have a bunch of form variation. If I go a little bit past the smallest I can get, and it will have form variation, and it will still fit in the card. But if my part gets to be all the way to the top and have any type of form variation, which is making a little bit surface variation, it will not fit into my envelope, which will make it fail my inspection process. That's why they call it the envelope principle. Perfect form at MMC. When your part comes at MMC, it better be perfect, because otherwise it will not fit in your envelope. Okay? If my part comes at LMC, which is the smallest I can get, I still have a tolerance zone that I can vary from. Therefore, I will allow for form variation. Hopefully that makes sense. Okay, this is a feature surface which will follow the envelope principle, which again it doesn't really account for the GD&T. Okay, so for form variation, how do you calculate it? Well, you put a granite table and then you put a diode indicator, which I forgot and left it in the lab. But pretty much it is just like let's call it like a diode. And this guy here, this guy actually just presses on the material, and it goes up and down. And as it presses on the material, actually maybe I can find one online. Look for a diode indicator. Bullock code. Inspection diode indicator. It is just a thing that has like a diode. And then you press on it, you see like this one, it has like a diode. And if you press it, the diode moves. And then pretty much what it does is if you hold and you have that, and you press on the surface as you move across the surface, pause the video. When you go and you put the diode indicator, you want to ensure that the top part is parallel to the bottom. So that way you can do it, put the diode indicator, you move part back and forth. The diode indicator will tell you what is the motion of the bottom. You just press on it. And as you press on it, the diode will move. And as the diode moves, it tells me what is the variation of the surfaces or the form of the part as I go and I slide it back and forth. And if I just need to ensure that it's within 9 times of an inch in this case, related to datum A, which in this case is represented by the granite table. Professor Escalona, what's a granite table? Hopefully it doesn't crash again. Granite inspection table. Boom. It is just a table that is super smooth. It's like a baby smooth. It's like this. And then again, it's made out of granite. It's like kind of like your counter in your kitchen. But it is super smooth. And usually it has flatness within 1/10,000th of an inch. You can also account for axes, features of size, to be parallel to something else. For example, if I were to have a hole like the one that you guys see here, this is the side view, that's a hole, and within the hole it has an axis. And what they're saying is, I want to make, look here, it's calling out to the features of size. When you call out to a hole or something that is cylindrical to the size, you're actually calling out the axis. You guys know. You're trying to orient the axis. Orient the axis to phi tau related to datum A. Okay, so what is datum A? By datum A is the bottom. How do you control an axis? I'm going to ask you guys. Let me stop the share. Let's suppose that I have a surface. This is my part. Boom, this is a part right here. Boom, put it there. Okay? And I decide the bottom to be datum A. And then I have a hole. Or you have to see the hole. Right there, right? Which I point to it and I say, I want that hole parallel to the datum A. So let's disappear this part. The hole, it actually has an axis, which is right here. And then I'm going to ask you guys a question. Is this guy parallel to the paper? You guys answer me from the chat. Is this parallel from the paper? Somebody, BB, tell me, is this parallel from the paper? This is the paper which is datum A. Is this parallel? BB is sleeping. Yes, it's parallel. Is this parallel? Carlos, tell me, yes or no? Come on, guys. The quicker you tell me, the faster I move. Is this parallel? Yes, it's parallel, guys. This is parallel. This is parallel. That is parallel. All of it. In fact, I can go and rotate it. See, it's still parallel. Now, as soon as I tilt it upwards, then it's not parallel. So if I can go and I can keep it like this, I can literally rotate my axis 360. Right? As long as I keep parallel. So the way you control an axis to a plane, it's a little bit different than the one that I showed you before. The one that I showed you on the sketch, I'm not controlling the parallelism, I'm controlling the perpendicularity, how crooked the part is to the surface. So let's go back over here. You guys will notice that I went around 360, right? So the way you control parallelism of an axis for a plane, and again the plane in this case is the datum, it is by creating two parallel planes. And that is the reason why in the control frame you guys will notice that I don't have a diameter. There will be cases where I will have to have a diameter. For example, this one is, I am controlling a feature of size. I don't know I have a feature size because it has a dimension and then I put it there. As soon as I do it on a feature of size, it generates an axis. So my datum is an axis. And I am controlling another feature of size using parallelism. And I say parallel to datum A. So in other words, I'm controlling an axis to another axis. So do I need two parallel planes? Do I need a cylinder? What do I need? Okay, so the way they do it and they say is, you know what, in order for me to control this, so again, you're controlling the geometry imperfection of the parts, not the size, the geometry. That's why you call it G, or GD&T. So this is my axis, which is my datum. And this one over here is what I'm controlling, which is the axis. It's the axis of the whole. So they didn't say, hey, make a parallel. They say, actually, they say, make a parallel. So the way they made a parallel, they say, okay, I'm going to allow to make a parallel within a cylinder. And they allow the axis to move around, but they put it and they constrained it by a cylinder. So if you want to look at it from the side, the little cylinder where my axis needs to live has a diameter. Little cylinder right there. And that's why you go and you will see it on the feature control frame like an axis. Hopefully that makes sense. I don't want to go through the math. This is a little bit more advanced. I only cover it for people that actually want to get certified. If you guys are interested on this crazy thing, and you want to be certified by the ASME, I would say that take ETEC 34, which again, if you guys can take it. If you guys are taking engineering too. For let's call it for advanced manufacturing or precision manufacturing. If you want to work for an aerospace company or a laboratory, stuff like that, also you might want to take that class. Okay, we also, the same way that I control parallelism, and I control one surface parallel to another, so the datum is the bottom, the surface, just make a parallel, or we also went and we also did an axis to another axis. We can also control surface to another surface. So for example, in this case, I am pointing to the surface, so I have a feature of surface, and when I'm controlling a feature of surface, it's really easy to just go boom, boom. You just go, I want that surface being perpendicular to datum A within 12 thousandths. The tolerance zone, all it is two parallel planes. And my part form needs to live within 12 thousandths of an inch. You can also deal a surface, a feature of size to a plane. This is similar to the one that I showed you just a second ago. This one, but instead of doing like this, I did it like, well, that's how it looks on the slide that I'm showing you. But it's the same concept. You guys will notice that I have an axis that can be crooked and it has to live within a tolerance zone, which is a cylinder. Let me see if I thought I was make drawings. There we go. This is what it means. This guy is my datum, which is the red one that you see here. I am controlling the crookedness of my feature of size within a cylinder. So my axis has to be within that cylinder. How big is that cylinder? Well, the cylinder has a diameter of 0.003. That's what this number you guys see there. And then my axis again will have to live within it. Exactly the same way that you see here. The axis needs to live within this cylinder. Hopefully that makes sense. Now, you guys also will notice, I don't want to go too much into that, but it doesn't have, some of these feature control frames will have a name, some of them will not have a name. And again, it binds it back to one we call it regardless of feature size in the feature control frame. Or sometimes they call it material modifiers. It's called material modifiers. You will here inside of the feature control frame, you might put nothing. If it is nothing, it's regardless of feature size. You might put a little m. If you put an m, it is called maximum material condition. And if you put a little l, it's the material condition. Right? I think this guy is a surface. You guys will notice it's applied to the surface. And since applied to the surface, I got two parallel planes, and my point needs to be somewhere in there. How do I check it? I can check it with gauge fillers, or I can also with wires that have the diameter of this distance, right? Which in this case is 5 thou. So I can go and I can grab one of these gauge fillers, and put it in the middle. This guy right here on the bottom, this is a granite table. what you see there. This guy is an inspection angle. It's actually 90 degrees, super precise. I grab my part, I put it against it, I grab a feeler gauge, I stick it inside of it, and then I see if there is a little gap. Like I said, I can put a wire or I can put a gauge stuck. And that's how I know if it's a little bit out of angle. You can also, it seems to me, you can also grab a diode indicator, you can move it up and down. And again, because the diode indicator, as you press it, and you have a little thing that looks like this, and as you put it on the part, and will press on it. And then as you move all of this downwards, the diode indicator will move. I gotta read the total motion of the indicator movement as I go and I touch the surface that is in red. If it moves too much, that means it's actually cricket. It's supposed to be straight from where you start to where you go down, and don't have so much movement. If it has a lot of movement, that means it's I need to check the amount of movement that I'm allowed to do. And in this case, let's say that my part is allowed to move 5 tau. That means the total movement of my diode indicator as I went from the top to the bottom cannot change more than 5 thousandths. So this is similar. Actually, it's pretty much exactly the same thing that I did when I did the sketch, which is again this one, right? Which is allows you to now control the size and the form. And again, you don't have the size, but there should be a size over here, right? Plus and minus, whatever it is. This is the M. This is how, exactly what I told you before, you create a boundary so that you allow, okay, so this guy that you see here, this is exactly the example that I did in class. I'm not in class, but in sketch, this form. And I told it, this is just me putting it into words, by the way, okay? Just trying to explain it to you. I said your part comes a certain size, and it's also cricket. And in order for me to come for the worst case condition such that it fits, I have to design this hole for the worst case condition, and I also have to design for the pin for the worst case condition. So we create something that we call it boundaries, like virtual boundaries. We call it virtual conditions. The virtual condition will allow me to look for the worst case condition. And the way we say it in terms of GD&T vocabulary, and we say this one here, the one on the top, is the D, plus and minus, right? Your regular dimensional tolerance. And then I tell, using my feature control frame, that's how I speak it. I say that I have a feature of size. Say, putting it right next to the diameter, which is a feature of size. I am going to graph this feature of size, which represents an axis. And I'm going to control the axis within a diameter, which has 6 thousandths when it comes to the maximum material condition. So this is why it's kind of like an if and else statement. If your part comes at MMC, which in this case, MMC for the part is 0.377, that's the maximum material condition. If your part comes at MMC, I am going to give you 6 thousandths. What happens if I move away from MMC? Let's find out. Here's my part, right? And then I told you that my part has a certain diameter cylinder where my axis needs to live, right? And that happens at the MMC, at the worst case mating condition. However, if my part gets to move away from MMC towards LMC, let's say I got it smaller, my part will not look like this. Let's say I want to make it smaller, I want to make it about here. Before it used to be big, right? Now I'm going to make it smaller. When I made it smaller, I pushed it away from MMC. Now it's at LMC, which means now I have more wiggle room. In fact, look at this. There is a little bit extra that I'm allowed to be more cricket. In fact, I can tilt it a little bit more. This little bit more is what we call a bonus, because I move away from the biggest I can get. Now it's a little bit smaller. Because I got a little bit smaller, that means my part will have now more wiggle room to fit. Therefore, it's called a bonus. In fact, we call it bonus tolerance. What is the bonus tolerance? How far away you move from the MMC. In this case, because I have an external feature from it is how far I got them from the biggest I can get. And again, it's because I went from MMC to LMC. Mathematically, again, you guys even notice a BC right there? That is what the BC stands for, the virtual condition. The biggest I can get plus the quickest I can get. What is the biggest I can get? 0.377. The quickest I can get. Well, at 6 tau. That's what you guys see here, at 6 tau. And I will give you your maximum boundary. What is my maximum boundary, Professor? What is this one? The big one. The blue one, which became the virtual condition. The virtual condition is telling me the worst case condition. However, as my part deviates from the maximum material condition to the least material condition, my part gets smaller. For an external feature, it gets smaller, allowing for a little bit more, which is bonus. I can use that bonus for making it more crooked. Add bonus tolerance for geometric imperfection. Which is exactly what I told you. Right? This is what I say. You go and you make your picture condition, and then I can go and I can check it. If I want to actually do this for reals, like to check if I had, I most likely will have to put it on a computer that touches the part and it generates like a model of what the part is. Or I can go get myself a gauge. This gauge is a special gauge. It's a gauge that it gets manufactured by different standards, actually a more strict standard than the ASME Y40.5. And what it does is pretty much allows you to say, you know what, I'm going to make a gauge which is going to be the size of the virtual condition. Then make that gauge to that size such that if I have a part that came at MNC, it will barely fit. And if the part is less crooked, let's say it's straight, it will fit. If it's bigger, it will fit. So all the worst case conditions it will be encountered by the gauge, as it will have a combination of G and D, geometric imperfection and dimensional imperfection. And I'm able to check the behavior of my part like this, as I'm able to go and grab 1,000 parts of them, go get my gauge that has the size of the virtual condition, go and put it inside of it, and boom. Hopefully that makes sense. Okay, so I think this is what we're gonna do, because it means GD&T, to be honest, is pain in the butt. Okay, so this is how you guys are gonna learn. Tomorrow when we meet, we're gonna start doing quizzes like crazy. Hopefully, after so many quizzes, you guys will start getting the hang of it. But if you guys want to really grab the hang of it, you need to understand first fits and tolerances, such that when we talk about GD&T, you then can focus on GD&T, not on tolerances. Again, we will do a quiz tomorrow. Ask questions, as much questions as you can ask, because I don't know if you are having problems. Step at a time, maybe sentence at a time. I didn't understand what you said. Repeat it different way. Okay. Let me stop the video.